Hey guys, this is Patrick from STH. Today, we're going to do one of the most exciting things that I can think of, and that is really to look at all of the new Hopper and other announcements that came out of NVIDIA GTC 2022. If you don't know, this week we had the GTC 2022 conference, and at the keynote, Jensen got up and he basically unloaded on the world a bunch of hardware that's really the next generation hardware that'll start really like in the second half of this year and going into 2023 and kind of beyond that as well. So what's really cool is that we actually got a ton of hardware announcements. And if you don't know this, Jensen basically has three things that he does in his keynotes. First, he always tries to do some kind of inspirational, aspirational message and kind of weaves that throughout. The second thing that he does, if he has new hardware, is he presents that new hardware, which is what we got this year. And if he doesn't have new hardware, he usually takes the existing hardware and says how great it is again, and then tries to weave that into some of the aspirational messages. But those are basically the three things that we typically see in GTC. And for this one, we actually got a lot of new hardware. And so what I thought I would do is let's go through the keynote. And instead of going through the entire hour and 40-minute keynote, because that's super long, what I did was I just actually clipped out all of the hardware announcements, or the ones that I thought were interesting. And then what we're going to do is we're going to talk about those and talk about the keynote. Because there are definitely some things that you have to do whenever you listen to an NVIDIA keynote. There's definitely, especially in the data center side, a lot of stuff that you have to kind of read between the lines. So I'm going to hopefully provide some of that context. And also, there were a ton of little Easter eggs in this whole GTC keynote thing that I think a lot of folks just totally whiffed on and didn't see, must have just missed or whatever. And so I want to call those out so that way everybody can see. And before we get too far in it, although this video is not sponsored by NVIDIA, we do have a sponsored giveaway that is going on the STH main site for GTC 2022. We're not doing this video as part of that, but they send a GPU. And if you want to win it, well, go to the STH main site. You can enter. We'll link that in the description, but totally check it out. And that giveaway is only going to be open for a short period of time after this video is going to go live. So if you're subscribed, you're probably going to be able to get a chance to enter. If you're not subscribed and you're watching this like a week later, you're not going to have a chance. So it's a good reason to go and subscribe. With that, let's get over to the keynote and let's get to it. Okay, let's get to the big one here, and that is the NVIDIA Hopper, or the H100.
We designed the H100 for scale up and scale out infrastructures. So bandwidth, memory, networking, and NVLink chip-to-chip data rates are vital. H100 is the first PCI Express Gen 5 GPU and the first HBM3 GPU. A single H100 sustains 40 terabits per second of I/O bandwidth.
Okay, and just real quick, because I know a lot of folks don't necessarily see this stuff every day, what you're basically looking at when you see this H100 is this is only the actual package. It's not the entire SXM package that this would go onto, or a PCIe package that this would go onto. And what you basically see is that there are a couple different components and three big ones that we want to talk about. First, in the middle, that's the actual GPU die itself. Around that GPU die, what you're going to see is that there are 6 memory packages. These are HBM3, and something to just note that this has 80 gigabytes of memory. The third thing, though, is that underneath those, you're going to see this like kind of little layer that's underneath, and they call it 2.5D packaging, but really there's a silicon interposer on the bottom, and then basically you have the HBM3 and the die, the GPU die that's sit on top of that, and then that silicon interposer basically provides the wires you can think of the connection that goes between the HBM memory as well as the GPU die. So that's how that is all co-packaged together.
Let me highlight 5 groundbreaking inventions. First, the H100 has incredible performance. A new tensor processing format, FP8. H100 has 4 petaflops of FP8, 2 petaflops of FP16, 1 petaflops of TF32, 60 teraflops of FP64 and FP32.
So let's kind of dig into some of these performance things just a little bit and just kind of talk a little bit more about Hopper, because this was definitely the big announcement. This is something that actually wasn't in the keynote, but this is another slide that just kind of tells you a little bit of the overall footprint of the H100. We now have things like we have 132 SMs, we have 50 megabytes of level 2 cache. There's all kinds of new features like PCIe Gen 5. You also get Sharp, which is a kind of thing for NVIDIA's networking that we'll maybe talk about a little bit later. And then also you get things like new generations of NVLink and all the features that you get with a new generation of GPUs. This is definitely the successor to the Ampere A100 generation, and this is the overall layout. And then something you'll notice with these new SMs is that you actually get twice the performance per clock, and that's basically what this chart is. The one new thing, of course, is that you get FP8, and that is a new thing that we're going to talk about in a little bit that will help accelerate performance. But this is really one of the big things that's driving that performance improvement.
For AI processing, Hopper H100's 4 petaflops of FP8 is an amazing 6 times the performance of Ampere A100's FP16, our largest generational leap ever.
So something that I didn't know about, and here's the actual slide for it on that FP8, is that there are basically 2 ways you can do it. So you use 1 bit for the sign, but then you basically have the exponent and you have the mantissa. And the way that you do with FP8, because you only get like 7 bits for the exponent and mantissa, that basically means that you have to pick either 5 for the exponent and 2 for the mantissa, or 4 for the exponent, 3 for the mantissa. It turns out that depending on what kind of workload you're running, one of these 2 formats is actually better because of where the range of potential values are compared to something like FP16. And so because of that, what we were told by NVIDIA is that they can actually kind of, determine which one is best and use that, which I thought was like insane, but that's really cool. And that's also done a lot in software to be able to go and figure out which one to go use.
The transformer is unquestionably the most important deep learning model invented. Hopper introduces a transformer engine. The Hopper transformer engine combines a new tensor core and software that uses FP8 and FP16 numerical formats and dynamically processes layers of a transformer network.
So let's talk about the transformer engine. So this is one that is crazy because when you're watching the keynote, you think like, oh my gosh, there's like some kind of crazy core that's this transformer engine and that must be insane. But what we actually learned on a deep dive call about this a little bit later is that the vast majority of this whole transformer engine thing is actually happening in software, and then it's using the existing or the new tensor cores to be able to go and actually implement the thing. So this isn't necessarily something like you're going to go see like these just giant transformer cores or transformer engines sitting around in the actual die. This is actually something that is done mostly in software that goes into and actually uses the hardware more efficiently.
Transformer model training can be reduced from weeks to days. For cloud computing, multi-tenant infrastructure translates directly to revenues and cost of service.
Okay, so confidential computing is a huge area in the industry. You definitely see folks like AMD was actually pretty far ahead on this one. Intel has things like SGX for their secure enclaves. And basically the idea is that if you're running a workload on a cloud system, you don't necessarily want the cloud provider to be able to go and see all the stuff that you have. You may want to go create things like secure enclaves so you can be assured that other entities in that cloud thing, whether it's another tenant or the cloud provider, can't get in and see the data that's in there. It's really important for a whole bunch of areas. Think about like if you were doing something like medical records, you're doing AI inferencing on medical records, you don't necessarily want either somebody that's sitting in the box or whatever to be able to go and pull data out. And that's what this whole confidential computing thing is. And so it's really cool what NVIDIA is doing here. They're actually adding the ability to have confidential computing and secure MIGs in the Hopper H100. And if you don't know what MIG is, you basically can go and slice up a H100, and actually you can do it with the A100 generation. We showed this when we did some of the A100 reviews on the STH main site, but you can actually chop it up into multiple smaller chunks, so that way you can have some that are like big instances, some that are small instances, and assign different amounts of GPU resources to each of them. And with confidential computing and this MIG functionality, basically means that if you're a cloud provider, you can go and you can split the GPU in half, you can split it up into like 7 different segments, and then you can go give a different slice to a different customer, and all of those can be run using this confidential computing stack. And so even if you have 2 different users on the same GPU, you know that they're not basically able to go see, what's in that confidential computing thing, and the cloud provider can't see it either. And although I use medical records, frankly, a lot of the AI folks really don't want to share their algorithms and are really freaked out about their algorithms going to the public cloud because somebody could steal them or whatever, or just onto different boxes. And so this is something that also just the AI guys are like, yeah, we don't want to share our algorithms. So this is kind of nice that they have that as well.
H100 is the newest engine of AI infrastructures. H100s are packaged with HBM3 memories using TSMC's CoWoS 2.5D packaging and integrated with voltage regulation into a Superchip module called SXM. Let me now show you how we build up a state-of-the-art AI computing infrastructure. 8 H100 SXM modules are connected by 4 NVLink Switch chips on the HGX system board.
Okay, so this assembly that Jensen's showing here is actually something that you would call like the HGX H100 8 GPU. Now in the Ampere generation, we have the HGX A100 8 GPU, which we saw, I think we did reviews of the Supermicro and Inspur servers with that. Also in terms of Redstone would be the HGX A100 4 GPU, and the Redstone platform, we looked at the Dell PowerEdge XE8545. You can find that review, and also we looked at Supermicro systems with that as well. And so that would be the Redstone platform. NVIDIA actually sells the entire baseboard as an assembly to the server makers, and they also can use it in their own DGX systems as well. Something that you're going to notice on this, which is just sticks out at me at least, is that on the front, they actually don't have the NVSwitch heat sinks on there. They usually are pretty giant heat sinks because those things use a ton of power. The other thing you'll notice is that this particular system is a liquid cooled system. So these are not air cooled heat sinks. You're going to see that in the back, you can see that little copper pipe, and that is basically how liquid goes into this whole assembly. So these have water blocks on them or liquid blocks on them, and that's just something that is going to be different in this generation because we have so much more power consumption.
The 4 super high-speed NVSwitch chips have 3.6 teraflops of sharp in-network computing, first invented in Mellanox quantum Infiniband switches. For all-to-all reductions, used extensively in deep learning and scientific computing, Sharp effectively boosts bandwidth by 3 times. The CPU subsystem consists of dual Gen 5 CPUs and 2 networking modules, each with 400 gigabits per second CX7 InfiniBand or 400 gigabits per second Ethernet networking chips. CX7 has 8 billion transistors and is the world's most advanced networking chip. A total of 64 billion transistors deliver 3.2 terabits per second of networking. Introducing the DGX H100, our new AI computing system.
Okay, so this is actually really cool. They just blast through this whole thing, but we're gonna take a couple screenshots just to be able to show you real fast. If you look at something, the first thing we're gonna notice is that Jensen's saying, oh, these are Gen 5 CPUs. Now he doesn't actually say which CPUs they are, but a couple things here. One, you're gonna notice that on one of the sides of the system or one of the CPU sides, you see that we only have 8 DIMMs. And then the other thing is that this, if you look at the heatsink, I guess, mounting pattern and the retention, that looks a lot like the current Cooper Lake, Ice Lake, and also what we've already seen in terms of Sapphire Rapids cooling. And just also as one of the world's smallest things, as this thing is being exploded, you can also see the fact that on the rear of the chassis that there are 2 little inlets and outlets for liquid cooling. And then when you actually get to the back of the rack, when they show NVLink, you're gonna see that there actually are, an inlet and outlet port. But also what's interesting here is the fact that the CPUs and the ConnectX 6 NICs, NVSwitches, all that kind of stuff, that is all being cooled by air. So you still have a whole bunch of big fans, but you're basically moving, say, 8 GPUs, 700 watts each of heat out of the chassis just with liquid cooling.
Connected by NVLink, DGX makes the 8 H100s into one giant GPU. 640 billion transistors, 32 petaflops of AI performance, 640 gigabytes of HBM3, and 24 terabytes per second of memory bandwidth.
Hey, when you look at the data sheet on this thing, this actually does 10.2 kilowatts in a single system, which means that if you have 4 of those in your rack, you're basically gonna have a 40 kilowatt rack before you put any networking storage or anything else in that rack.
DGX H100 is a spectacular leap. And there's more. We have a brand new way to scale up DGX. We can connect up to 32 DGXs with NVLink. Today, we're announcing the NVIDIA NVLink Switch system. For AI factories, DGX is the smallest unit of computing. With NVLink Switch systems, we can scale up into one giant 32-node, 256 GPU DGX Pod.
And the reason that's important is that you actually only need like 2 layers of switching to be able to do 256 nodes. Whereas if you wanted to go scale out to like many more, you'd actually need to go and create extra layers in the switching hierarchy, which basically means you have more complexity, potentially more latency. And so this is a thing that when we asked NVIDIA, they basically said, yeah, the reason that we cap it at 256 in terms of this unit is because the switching for NVSwitch.
with a whopping 20.5 terabytes of HBM3 memory and 768 terabytes per second of memory bandwidth. 768 terabytes per second. Each DGX connects to the NVLink switch with a quad-port optical transceiver. Each port has 8 channels of 100 gig PAM4 signaling, carrying 100 gigabytes per second. 32 NVLink transceivers connect to a 1-rack unit NVLink switch system. The H100 DGX Pod is essentially one mind-blowing GPU. 1 exaflops of AI computing, 20 terabytes of HBM3, 192 teraflops of sharp in-network computing. The bisection bandwidth moving data between the GPUs is an amazing 70 terabytes per second. Multiple H100 DGX pods connect to our new Quantum 2 400 gigabits per second Infiniband switch with sharp in-network computing, performance isolation, and congestion control to scale to DGX SuperPods with thousands of H100 GPUs. Quantum 2 switch is a 57 billion transistor chip with the ability to connect 64 ports of 400 gigabits per second each. DGX SuperPods are modern AI factories. We are building EOS, the first Hopper AI factory at NVIDIA, and she's going to be a beauty. 18 DGX pods, 576 DGXs, 4,608 H100 GPUs. At traditional scientific computing, EOS is 275 petaflops, or 1.4 times faster than the fastest science computer in the US, the A100 powered Summit. At AI, EOS is 18.4 exaflops, or 4 times the AI processing of the world's largest supercomputer, the Fugaku in Japan. We expect EOS to be the fastest AI computer in the world.
Here's just a little bit of perspective about this, which is a little bit different. This thing is so big that, like, you have all these AI startups, and these AI startups like, oh, I have my little chip and like whatever. NVIDIA is just crushing folks in terms of, delivering consistent generational improvements in terms of AI training performance. And then they're not only just doing like, oh, here's a box, but like, hey, let's go scale out to like massive supercomputer scale. They're doing that too. And so that's really the thing that I think a lot of folks miss when they talk about like all these, AI startups that have like these little chips. I think that things like GraphCore, like how the heck do you compete with NVIDIA doing this kind of stuff where they're doing systems engineering at the scale and they keep coming up with just giant generational improvements, and the whole world's software stack already runs on NVIDIA anyway. I mean, like, sure, you can get some benefit maybe in some cases, but you're not going to go compete with NVIDIA head to head with a little chip that's, you're just not going to be able to do it. So just kind of something interesting that this whole thing just kind of made me think of. And also just if you're a reseller of high performance computing systems, man.
EOS will be the blueprint for the most advanced AI infrastructure for our OEMs and cloud partners. Partners can take H100 DGX SuperPod as a whole, or the technology components, at any of the 4 layers of our platform. We are standing up EOS now and will be online in a few months. Moving data in traditional servers overloads CPU and system memory and are bottlenecked by PCI Express. The solution is to attach the network directly to the GPU. This is the H100 CNX.
Hey, on this card real quick, something was really interesting. So I asked what the TDP of it is, right? Because, well, it's definitely not going to be the same as like the SXM modules. And what I was told is that this is a 350 watt TDP card with the ConnectX-7. The cool thing here is that you can do GPU direct communication. You don't need to go through the whole host thing, and that's the entire purpose of this card. NVIDIA did have some versions of this that weren't kind of, I guess, as widely used in the previous generation, but it looks like they're doing it again in this generation. I asked if this is Bluefield, and NVIDIA told me that this is not Bluefield. This particular one is not Bluefield, but they also told me that there is a version of the NVIDIA H100 PCIe card that does not have the ConnectX. If you just want to do the typical model where you just kind of plug a bunch of these into a system, you can totally go do that using a card. However, I do want to just quickly note the fact that the NVIDIA H100 at 350 watts, like there are a ton of systems that we review that are going to struggle with cooling 350 watts, especially when you start getting to 8 and 10 GPU configurations, right? I mean, that is just a absolute ton of power to cool. And frankly, like PCIe cards really were not designed, passively cooled PCIe cards are not really designed for that much. And the other thing that's really interesting in terms of this card is the fact that unlike one where you just have the GPU without the display outputs, which would be typical of a data center GPU, when you have a GPU that looks like this with the NIC involved, you still have to have the things like the cages for the networking and the optics. And so you actually are blocking some of the rear surface area. So not only are you increasing from 300 watts to 350 watts, you're also at the same time having to go and push more air through a smaller, I guess, channel because you have some blockage due to the optics and also the fact that you have the ConnectX 7 there.
An incredible amount of technology in a tiny little package designed for mainstream servers. Let me update you on Grace, our first data center CPU. I am pleased to report that Grace is progressing fantastically and on track to ship next year. We designed Grace to process giant amounts of data. Grace will be the ideal CPU for AI factories, and this is Grace Hopper, a single Superchip module with direct chip-to-chip connection between the CPU and GPU.
And I just wanted to see scale because NVIDIA really didn't show the scale of these. So I want to see, like, is this just a normal SXM module that has two of these things on it? But when I actually went and just kind of roughly sized the SXM module to the size of the Grace and just using that Hopper die and the HBM3 memory packages kind of as my kind of guide, this is roughly, it's not perfect, but this is roughly about the size of an SXM module with the H100 versus if you're going and looking at one of these Grace modules. So you can definitely see that these Grace modules are a lot bigger, and that just kind of makes you think like, hey, what's the packaging for these? Because it doesn't look like it's your normal SXM. Assuming everything this is actually to scale.
One of the critical enabling technologies of Grace Hopper is the memory coherent chip-to-chip NVLink interconnect, a 900 gigabytes per second link. But I only told you half the story.
Wait a second, Jensen, that's totally wrong. You only told us a third of the story because there's actually another thing that's in here that a lot of people just totally missed, and I have no idea like how everybody missed this. The only reason I knew actually was because I knew that this was coming and I'd heard about it for some time, but probably the most exciting product that Jensen's actually showing here, he's not even talking about. So we're gonna go through the next part, but then I wanna go get to the third one because that's definitely the most exciting.
The full Grace is truly amazing. The Grace CPU can also be a superchip, made up to two CPU chips connected coherently over NVLink chip-to-chip. Grace Superchip has 144 CPU cores and an insane 1 terabytes per second of memory bandwidth, over 2 to 3 times the top Gen 5 CPUs that have yet to even ship. We estimate the Grace Superchip to have a spec-in 2017 rate of 740. Nothing close to that ships today. And the amazing thing is the entire module, including a terabyte of memory, is only 500 watts. We expect the Grace Superchip to be the highest performance and twice the energy efficiency of the best CPU at that time.
Hey, I just want to interject right here because something that you're going to notice is that there's this spec-in rate of 740 estimated. So number one, I don't think this is estimated because they haven't officially submitted it yet. But number two, 740, Jensen's saying like this is crazy performance, but it's really not. So just to kind of give you an idea, if you like R2 AMD EPYC 7773X chips, this is Milan X that we just did our last video on, those chips, these two chips combined, we're getting about 830, so that would be estimated as well because we're not officially submitting them because we're not allowed to with our license, but we get about 830 in terms of spec in, but there are vendors that are over 850 with these two CPUs. Some of the vendor teams just have better BIOS tweaking and stuff, so they can usually get higher than we can. But, these are basically a 2021 chip that had a little update for 2022, and they are nothing compared to like Genoa and Bergamo. I mean, core counts are going to explode after these 64 core chips. So man, it's kind of hard to say that that's like like crazy number in terms of spec in. Now the fact is it is on one module, but then Jensen says that it's 2 CPUs on one module. So I mean, I don't know. I don't know exactly what's going on here. Also, I just don't understand this whole nothing close to this ships today line. I don't know. I think like if someone said you get like 10, 20% more performance for like 10%, 12% more power, like to me, I don't necessarily know that I would say nothing close to this. It kind of feels like you could make an argument that that's pretty darn close, but maybe he's saying that because they're in the same package, but you have a 500 watt package, so do you really care how many packages you have? I don't really know exactly what that's going on here, and there are 2 CPUs on that package, so like, again, I really don't know how they're substantiating this claim. My guess is that they're either doing one of 2 things. One, they're talking about total memory bandwidth of that package, because you have 1 terabyte per second, but that would be like 2 CPUs of, today, and then also Gen 5 generation when this comes out in 2023. So maybe they're talking about memory bandwidth, but my hope is that what's really happening is that they're talking about some kind of acceleration, not necessarily the integer performance, because otherwise, I don't know like how the heck you can substantiate this claim unless there's something that they're not showing us really on this slide, or maybe it's memory bandwidth compared to today. I don't exactly know. But this is a little bit hard.
The enabler for Grace Hopper and Grace Superchip is the ultra energy efficient, low latency, high speed memory coherent NVLink C2C link. With NVLink that scales from die to die, chip to chip, and system to system, we can configure Grace and Hopper to address a large diversity of workloads. We can create systems with a 2 Grace CPU superchip, a 1 Grace, 1 Hopper superchip, a 1 Grace, 2 Hopper superchip, and systems with 2 Grace and 2 Hoppers, 2 Grace and 4 Hoppers, 2 Grace and 8 Hoppers.
Okay, I don't know if you just noticed this, but this is like the biggest secret of the entire thing, maybe, right? This is 1 Grace, 2 Hopper, and this is basically sitting in the middle slide, and he says it, but if you actually go and like he just kind of keeps going, he doesn't stop on it, he just says, oh yeah, we can keep scaling up to like 8 Hoppers, and like, okay, cool, but there is definitely something crazy going on with this thing. So let me just take that little image and let me blow it up. And if you look at what's going on here, you definitely have the single Grace, so the ARM CPU, plus you have 2 Hopper H100s. You can see the 6 HBM packages and the dies and all that kind of stuff there. And so this thing, you might just say like, oh yeah, whatever, who cares? But like, look at this actual like board that it's on, right? It's number one, not symmetrical. And most of the time when you see folks make just kind of like theoretical things, they tend to be very symmetrical because it just kind of looks better. But when you look at this, I mean, this looks like you can see like some power and data connectors on one end, and then on the other side of this thing, you can see that there's like these 4 blocks, and each of those 4 blocks looks like there's like 8 wires or fibers or something coming out of them on the other end. I mean, guys, to me, this is by far the biggest announcement, because this thing looks like it's ready to go get deployed, or it looks like it's an assembly from a supercomputer design that like that's exactly what this thing is. But in the keynote, he basically just says it and keeps moving on. And yet, look at this thing. Like literally the first day of coverage, like almost nobody covered it. We covered it just because I knew that this thing was coming. But I mean, oh my gosh, like he just glossed over it. But this is like a little supercomputer design nugget that's an Easter egg in this presentation. And one of the things that NVIDIA does have is this NVLink chip to chip. And so they're basically saying, hey, we're going to go open up to integrations. That's really important, especially when you get to the cloud provider side, because the cloud providers are saying like, hey, we want to go and do some customization of chips. And so this is something that NVIDIA can do to go tell a lot of the bigger customers like, hey, if there are specific bits of IP or something that you want to go add in, you can go do that. And here's going to be our interface for it. So it is kind of nice that NVIDIA is opening up with this.
Just as we have DGX for AI, we now have Ovx for Omniverse. The first generation of NVIDIA Ovx Omniverse computer consists of 8 A40 RTX GPUs, 3 CX6 200 gigabits per second NICs, and dual Intel Ice Lake CPUs.
You may have noticed that last week on STH, we actually did a review of the NVIDIA A40. If you think that's a coincidence, probably not.
And the NVIDIA Spectrum-3 200 gigabits per second switch fabric connects 32 OVX servers to form the OVX SuperPod. Most importantly, the network and computers are synchronized using precision timing protocol, and RDMA minimizes packet transfer latency. Today, we're introducing the Spectrum-4 switch at 51.2 terabits per second. The 100 billion transistor Spectrum-4 is the most advanced switch ever built. Spectrum-4 introduces fair bandwidth distribution across all ports, adaptive routing, and congestion control for the highest overall data center throughput.
Okay, this one is super cool. This is a Spectrum-4. This is a 400 gigabit per second switch, but it's actually a 51.2 terabit per second class switch. And that means it's like 4 times the total bandwidth of the Innovium switch, the 400 gig 32 port switch that we looked at on STH a couple of, I guess, months ago, quarters ago, back in 2021.
With CX7 and Bluefield 3 adapters and the Doka data center infrastructure software, this is the world's first 400 gigabits per second end-to-end networking platform. And Spectrum-4 can achieve timing precision to a few nanoseconds versus the many milliseconds of jitter in the typical data center. Today, we're announcing Hyperion 9 for cars shipping starting in 2026. Hyperion 9 will have 14 cameras, 9 radars, 3 lidars, and 20 ultrasonics. Overall, Hyperion 9 will process twice the amount of sensor data compared to Hyperion 8, further enhancing safety and extending the operating domains of full self-driving. Clara Holoscan is designed to the IEC 62304 medical grade specification and for the highest device safety and security level. The amount of computation in Holoscan is insane. The core computer is Orin and CX7 with an optional GPU, and the new Isaac Sim on Omniverse. First, Isaac Nova, like Drive Hyperion, is a reference AMR robot system on which the entire Isaac stack is built. Nova has 2 cameras, 2 lidars, 8 ultrasonics, and 4 fisheye cameras for teleoperation. We're announcing Jetson Orin developer kits are available today.
But in the final sequence, there were 2 little tiny Easter eggs I wanted to call out as well. So Jensen?
Engage.
The first one is that if you actually look at what's on the screen, they're actually launching an NGC container here, which I thought was kind of fun. It's just in the corner. I don't know why I thought it was fun, but that's what they're doing. And the other one I think is interesting is that somewhere kind of later in the last segment, these 2 cards just pop out and they pop their chips out at you. But something that you'll notice is that these chips don't have on-package memory. The memory is actually sitting on the PCB, most likely with something like a Bluefield or a ConnectX chip or something like that on it. But whatever the heck these chips are, it looks like it's either an Ampere generation GPU. This may be an Ampere generation combo GPU, or it might be a Hopper, future product, but this doesn't necessarily have the HBM memory. So I just was like, that's interesting. And that's our really last one. Hey guys, I hope you thought this look at GTC was super cool. I know I did. And I just kind of want to go through some of the really cool hardware that's in there. Now, all the stuff that we are, being presented with, I think Orin is coming out pretty soon, but the vast majority of this stuff is really kind of later in 2022 and into 2023. For example, like Grace isn't going to be till 2023, and they're saying like production is going to start in 2023, which means a little while till we see systems. And so that's just something to keep in mind there. And then when you talk about the Hopper generation, well, if they are using Sapphire Rapids or another PCIe Gen 5 CPU, we have to wait until those get launched till we can see that in a DGX system. And so my guess is that that's second half of this year as well. And there are a whole bunch of other things that just kind of need to happen to be able to get this technology out. But it was really cool to see in this GTC 2022 that there's so much new technology coming out of NVIDIA. I'm super excited for it, and I hope you are too. And hey, if you like this video, well, why don't you give it a like, click subscribe, and turn on those notifications so you can see whenever we come out with great new videos. We have a ton of crazy stuff coming out that I'm super excited about. And as always, thanks for watching and have an awesome day.